Sorry if that was a lot, but you don't need to know it in depth in order to do this next part, which is the meat of this, which is how to calculate heat transfer. You can put all this information together in one simple math formula. The information being that the amount of energy it takes to heat up or cool down an object, it depends on the mass of the object, the specific heat capacity of that chemical, and then how much you want the temperature to change. To heat it up by 1 degree doesn't take as much energy as to heat it up by 100 degrees. So, the amount of energy it takes to heat up or cool down an object, the energy it takes, the thermal energy, gets the symbol Q, and we call it heat energy. The unit is joules. Mass gets the symbol M, and its unit is grams. Specific heat capacity, it gets a symbol C, and the unit is joules per gram per degree, but once again, don't worry too much about it right now. Just ignore it if it bothers you. Finally, how much you want to change the temperature change, this gets the symbol triangle T. So in my exothermic and endothermic video, I talked about the triangle as a delta. It's a Greek delta, and it's the way that scientists symbolize the change in something. So this means the change of temperature, triangle T. The unit is degrees. This fact that the amount of energy it takes to heat up or cool down an object depends on how much you have, the kind of thing it is, and how much you want the temperature to change, we can symbolize with this math formula. Q depends on MC and delta T, triangle T, which means the heat energy is equal to the mass times the specific heat capacity times the change in temperature. So the heat energy involved in a temperature change is equal to the mass of the object times the specific heat capacity of the object times the change in temperature. This is a little bit tricky. If the object gets colder, then you lose energy, so Q is negative. And you also go down in temperature, so delta T is negative. So if you lose energy, Q and delta T will both be negative. If you lose energy and you get colder, delta T is negative. That's negative when you get cold. It indicates that you lose energy. If the object gets warmer, for example, you heat something up from 0 to 100 degrees, then that's a positive number. It goes up, and then that's a positive number too, because I gain energy. And this indicates that you gain energy to get warmer. So finally, example problems. This is the point of the video. If the rest of it was confusing, I was mostly just teaching you ways to understand the concepts that come up here. So if you didn't get any of the previous things, but you can follow me for these problems, then that's not ideal, but it's good enough. A 12-gram chunk of copper, and copper has a specific heat capacity of 0.38 joules per gram degree Celsius, heats up by 10 degrees. How much heat did it absorb? How much heat do you have to give the copper to heat it up by 10 degrees? This is the formula we're using. Q equals M times C times delta T. Heat is mass times specific heat capacity times the change in temperature. So we're going to take these facts and plug them into this formula. First, 12 grams. That's a mass, so it goes in the M. 12 grams, 12 is the mass. Next, this says it has a specific heat capacity of 0.38. So the symbol for specific heat capacity was C, and we replace a C with 0.38. Finally, it heats up by 10 degrees. So heats up, that lets us know that it's a positive number, and 10 degrees, that lets us know that it's a positive 10. So delta T becomes positive 10. I want to know how much heat this object absorbed, and heat is Q. So Q equals 12 times 0.38 times 10. I can put this into a calculator. Google is a calculator too if you need to. And it tells me that Q equals 45.6. So my answer, the amount of heat I absorbed was 45.6 joules. That's how much energy I have to give 12 grams of copper for it to heat up by 10 degrees. The second problem, the last one, say I have a 500-gram chunk of ice, so I have half a kilogram of ice. And ice has a specific heat capacity of 2.1 joules per gram degree Celsius. So this ice gets colder. Maybe it starts at 0 degrees and it ends at negative 23 degrees, but it cools down by 23 degrees. How much heat energy does it absorb or release to make this transition, to cool down? Our formula is Q equals M times C times delta T, mass times specific heat capacity times the change in temperature. These are the numbers, the facts that we need to plug into this formula. So 500 grams, that's a mass. That means the M gets replaced with the number 500. It says the specific heat capacity is 2.1, so that goes where the C is. Finally, it cools down by 23 degrees. Now, this tells me that for delta T, I put negative 23. cools down, it gets colder, that means it's a negative number because the temperature decreases. The delta T is a negative number because the temperature went down. The object lost temperature. Finally, I gotta calculate Q, the heat energy. So what I do is I multiply 500 times 2.1 times negative 23, and I get negative 24,150 joules. This is not wrong, even though there's a negative number. The negative sign just means that the heat energy in the object went down. That ice lost thermal energy as it cooled. So this means that the ice loses 24,150 joules of energy to decrease in temperature by that amount. So if you could do those last calculations, you got the point of this video. If you can understand them, it's even better. But in science, much of the time, you learn a lot of theory, and it doesn't make too much sense, and then you learn how to solve a kind of problem. And it doesn't make sense why you're doing what you do, you just plug numbers into specific places. But if you do it enough, and you think about it enough, those problems will serve as a diving board. You can use them to jump off into understanding the theory better. So ideally, you would understand the theory and the problems. But if you couldn't understand the theory too much, and you understood how to do those problems, that's good enough for me right now. I hope this is helpful.